anything else, I'll let you know. We're going to go ahead and get started. If you have any other questions, shoot them on the chat. And as I get going sharing my screen, if I'm not checking the chat as regularly, just unmute yourself and ask me that way as well. So, okay, I'm going to share screen. Okay. Hopefully you guys can see my screen now. All right. So as I mentioned last week, I like to start out new lectures with a new hiking picture. And this one is actually not even on our continent. It is on the great continent of Africa, which, fun fact, you may or may not care, probably don't, but that is where me and my husband met. We met in Africa. We are both native Arkansans, grew up in Arkansas, our cities are maybe half an hour apart, and we met in Africa, in Kenya. So Africa has a kind of special place in our lives. But this is an inactive volcano near Nairobi, which is the capital of Kenya. And we actually got to go hike the rim of it. So that big circle all the way around, I got to go hike it. It was back when I was in college. I spent the summer in Kenya. And anyways, me and the group I was with, we got to go hike this, and it was incredible. I mean, you felt like you could see, obviously you couldn't, but you felt like you could see the whole continent of Africa, or the whole country of Kenya from the top of that. And so really beautiful hike. But again, just another encouragement for you guys to start getting out. We actually went hiking this weekend as well. We went to Petit Jean and did the Cedar Creek Trail, and that's a really, really fun one. If you haven't hiked much at Petit Jean, it's really close by, and there's lots of good trails to do there. Okay, let's get into it. Measurements. So we are going to start talking about how to write out numbers and units, how to manipulate those things. And what we talk about today, you are going to use all semester long. So grab your cup of coffee, make sure you're engaged all throughout lecture, and ask me questions if you run into anything. So let's fill out this first slide. Physical quantity is this first blank. And let me make sure that this is not too big. So we're talking about physical quantities. We talked about matter last week, and we said chemistry is the study of matter. And as we study it, we realize too, matter is all the time changing. And so we have to be able to assess how it changes, and that's why we take measurements. And so when we're taking a measurement, we're assessing a physical quantity, which is a physical property that can be measured. All right, examples, we mentioned some of these last week, but you can measure mass, you can measure length, you could measure volume, I'm going to abbreviate, or temperature. These are all things you can measure, plus there's more. But when we take a measurement of this, oftentimes we do it before and after a change. Not only are we determining a physical property that the matter has, but we are looking at the starting and the stopping point. So measurements tell us the starting point for a property. And then also if you took a measure afterwards, that would be the kind of the ending point for that particular property, whether you're talking about the size of it, the volume, the mass of it, or whatever. And then here's the most important part of this slide is this last statement down here, that a physical quantity is described by both a number and a unit. And I'm going to put that in all capitals because that matters an exponential amount to me, numbers and units. The next slide, I'm going to illustrate to you with a silly example, but I'm going to illustrate how important units are. We use them in our everyday lives. And they're even more important in chemistry. So if I tell you the statement, if I say I'm 66, you don't know what I mean unless I give you more information, okay? Most of you might think age, okay? So you might think that I'm 66. The unit here would be years. That would be our unit, a unit of time, okay? I could also mean that I'm 66 feet, which I am not. Some of you met me yesterday. This would not be my profession if I was 66 feet tall. Or I can mean that I'm 66 pounds, all right? Which I am also not. unless you're in like 4th grade. Okay, so all that to say, numbers are meaningless without units. Okay, numbers are meaningless without units. And so I'm about to harp on this really big. If you start doing that dry lab, you Group B people, and even you Group A people now that you're done with your wet lab, and you work things out and you don't put a unit on every single number, there's some problems on that dry lab. You have to upload a picture of your work so that I can grade it and see how the process and the steps you use to solve it. If there are numbers on there without units, I cannot give you full credit for that. I won't do it on an exam. I won't do it on assignments. I can't, because I don't know what you mean. Even if you get the right number, and I may be able to follow your work because I know how it should be solved, you have to put units on every single number, okay, in this course. So I know it takes a second of time to do that, but please be diligent in that, all right? Please be diligent with units. Some more about how important units are. We've mentioned this. They tell us what we're measuring. They give a reference point. I'm going to give you another little illustration for this. When I was in grad school, there are people from all over the world in my department with me, in the chemistry department. And one of my best friends, we became best friends, she's from Iran. So I have learned and grown to love the Middle East and their food. They have really amazing food. But she, over in Iran, they measure temperature in Celsius. And, you know, over here, the common way we measure it was with Fahrenheit. So I know from all the science classes that I've had, I've grown to understand that 20 to 21 degrees Celsius is roughly room temperature, okay? Now, at home, my thermostat, I might keep it around 70 degrees Fahrenheit, right? We understand that around room temperature. We know we know sunny and 70 or sunny and 75. It feels really good, right? So if I understand that 20 degrees Celsius is room temperature, and I ask her, hey, you know, how's your family doing in Iran? What's the weather like over there right now? Well, it's August. If she tells me that, oh, it's 50 degrees Celsius in Iran today, because I know that 20 degrees Celsius is room temperature, I understand, holy smokes, like 50 degrees Celsius is flaming hot. That's really hot. And I'm glad I don't live in Iran right now. Okay. So that's what I mean when it says it's a reference point. When you understand certain temperatures or certain units, that helps you translate things without even doing a math problem. You can just common sense understand, okay, that 50 degrees Celsius is a lot higher than 20. That's really hot. But if you didn't know that 20 was room temperature, you might not know what 50 degrees Celsius is. All right, now in the sciences we use, I'm going to zoom in so I can write smaller, metric and SI units. Now, what does SI stand for? It's a system of international units, okay? System of international units. And let me check the chat really quick. Next week. So for all of you that left, do we still have to do the dry lab? I'm confused. I'm going to answer this question on the chat really quick. It says, for all the people that did wet lab yesterday, do we still have to do the dry lab? You do, but it's not due until next week. Essentially, you did the wet lab this week while the Group B people are doing the dry lab this week. And next week, if you'll look at the lab schedule, it has it all typed out for you. Next week, the Group A people who did the wet lab this week, you will do the dry lab next week. Okay, but you're welcome to start on the dry lab at any point. You don't have to wait until next week if you want to get started on it. Okay, but it's not due until September 4th for everyone, Group A and Group B. Hope that clarifies. All right, back to units. In the science, we use metric and SI. So you guys, mostly for this class, we're going to use metric units. But I want to ask this question, and feel free to unmute yourself here if somebody has an answer. Why would we need a system of international units? Why would that even be important? What do y'all think?
So that scientists like worldwide can understand each other.
Exactly. Okay. Let's say we're all working on a vaccine for the coronavirus, right? Surely we're not the only country doing that. Well, if somebody gets to it first, you know, it's helpful for them to share exactly how they made it. And if we don't have the same types of units that we can communicate that with and use that as a reference, you know, we can't further science, we can't further medicine, we can't share what we've done worldwide. So that's why that's important. To have an international system that everybody knows what those units mean and can convert them to, you know, the metric system or other systems that they want to use. That was particularly important back in kind of the space stage, back in the 50s, 60s, 70s. I mean, it was almost a race, right, to see who could get to the moon first. But anytime scientists publish articles or things like that, you're oftentimes going to use SI units so people can reproduce the research that you've done. All right, if you look at this table, it shows you what quantity we're talking about, okay? And then it shows you this first column, what the SI unit for that would be. Next column, what the metric unit is. And then if those two are different, which oftentimes they are, it shows you how they're related. So for example, we look at this first one, mass. If we're going to measure the mass, well, in the SI system, the unit is the kilogram. In the metric system, the unit's the gram. Which one's bigger? I don't know. Let's look at this. It says 1 kg, which is 1 kilogram, equals 1,000 grams. So a kilogram is bigger by 1,000. All right, and then it gives you others as well. So the meter is the same for both. For length, we use meter internationally and in our metric system. Volume, we're going to go into depth on this, but you can measure volume as a cubic distance because a meter is a length, right? It's a distance. So a cubic meter is a measure of how much space something occupies. That's a volume. Or we have the metric unit, which is the liter, okay? And then this shows you how those two are related over here. And then it shows you Kelvin for temperature. We're actually going to talk about temperature more on Thursday, so we'll come back to Kelvin and degrees Celsius. And then you see that for time, it's the same second unit of seconds for both. All right, so today, so far, we've talked about units and why they're a big deal. Now, second thing we're talking about, we're transitioning, we need to know scientific notation. So because this is a chemistry class and we're going to do some math all throughout the semester, we need to know how to write numbers in scientific notation and then how to also convert them back to standard notation. And if you need to add, multiply, subtract, divide numbers in scientific notation, that's what we're going to go over. So why is scientific notation important? This first statement right here says why. It's a way to make really small numbers or really large numbers more manageable, okay? I don't know about you, but when I see a number with 100,000 zeros on it, my mind can't comprehend how big or sometimes how small that number may be. So scientific notation helps us with that. And here is the general format. I know it's letters, which you're going to have to get used to letters and numbers together in this class. But general format is that you have some base number A, okay, and then it's times 10 with an exponent. So B is the exponent, and A is your what I'm calling your base number. All right, and then it tells you further, A has got to be a number between 1 and 0, or 1 and 10. A has got to be a number between 1 and 10. So it cannot be, like it could not be 0.8, right? That's not a number between 1 and 10. It's got to be a number between 1 and 10. And so our base number will have to, it can have decimals afterwards. It could be 8.3 or something, but it has to be a number between 1 and 10. And then B, this is actually the number of places that the decimal moved whenever you were converting from standard to scientific notation, okay? But this is your exponent. All right, so we're gonna do a couple examples right here. I'm gonna zoom in on these. We have this large number, 83,910. I wanna convert this. This is a number written in standard form. I'm going to convert it to scientific notation. And I'm actually going to erase because I want to watch. Right now, if I were to put a decimal in on this number, where would I put the decimal? It just as a standard number.
In between 8 and 3.
Well, that's as a scientific notation number, but as a standard number. When you're right, Abby, that when we convert it, it will be between the 8 and the 3. But right now, just as a standard, for us to know, it's 83,910. What was that, Brennan? After the 0. So here's the decimal right here. So if we're going to convert this to a format, we've got to make this number a number between 1 and 10. So I've got to move the decimal until, like Abby mentioned, it is 8.3910. Now that's a number between 1 and 10. So I'm going to write that out, 8.3910, and then we've got to count the number of places the decimal moved. Well, it moved 1, 2, 3, 4 places. So that's going to be our exponent, times 10. And here, for this example, it's a positive 4, okay? If you did 8.3910 in your calculator times 10 to the power of 4, you would get 83,910. Now, this also brings up kind of a general rule. You may not know exactly how to write it out, but what this means is we move the decimal towards the left, right? we moved it left. So anytime you move the decimal left, what happens to the exponent? The exponent increased, okay? So initially, well, we'll just write that out. If you move the decimal left, then the exponent increases. That's the rule here that we learned. Now notice I didn't say the exponent becomes positive. Here in this case it did become positive, but there may be times it increases but it's still a negative exponent. So just say it increases if you move it left. All right, let's look at this second number, 0.000596. So we see our decimal this time. If we want to make this a number between 1 and 10, I'm going to move it towards the right. So I'm going to move it this way, and if I stop right here, I have 5.96. That is a number between 1 and 10. Now we need to count how many places did the decimal move. 1, 2, 3, 4. However, we moved the decimal the opposite direction. We moved it to the right this time. So when you move it to the right, the exponent decreases. So this is going to be a -4, okay? So we're going to write our little rule the way we did for the first one. If the decimal moves right, the exponent decreases. Questions on that? Okay, good deal. So we're actually going to practice this a little more on the next page. So I'm gonna just shut up for just a second. I want you to write these numbers out. If you don't have the slides, just write them on a sheet of notebook paper. And I'm just going to watch the clock. I'm going to give you all just a minute or two. I want you to just do the first two right now, and then we'll handle the next two. So just do the first two numbers, and then we'll do them together. So these are standard written numbers, and I want you to convert them to scientific notation. Okay, maybe you've at least got one, if not both of them done. So we're gonna look at these first two. Also, if you jumped on the Zoom late, make sure your name as it appears on your screen is your first and last name and not like an abbreviation. I mentioned this earlier, but some of you may have missed it. That for attendance purposes, that helps me. If you just put your initials AK or CD or whatever, I'm not gonna know who you are. So make sure I see your name, because when I download the attendance file, that's important for me. So let's look at this first one, 65932. So the decimal would be right here after the 2. We're going to convert it to a number between 1 and 10. So I'm just going to move the decimal until I've got, okay, 6.5932. And I move the decimal 1, 2, 3, 4 places. So that's times 10. And here our exponent increases, so it's a +4. Any questions on that? Anybody get anything different? Okay. We'll do the next one then. This is a really small number. If we're going to convert it to scientific notation, we're going to have to move the decimal to the right. And remember, our exponent's going to decrease. So I'm going to move it 1, 2, 3, 4, 5, 6, 7 places to the right. So you should have 8.37 times 10 to the -7. Okay. So that's converting standard to scientific. Now let's do the reverse direction. So take another minute, convert these scientific notation numbers to standard notation.
Whenever we are doing these, do you want us to do 3 significant digits or no on the converting to scientific notation?
I'm going to let y'all know something. Don't tell anyone. I don't really care a whole lot about sig figs.
Okay, good.
You can celebrate that if you want. So just give me the number of decimals that like, well, like you saw on these first two numbers up here, I put all the numbers, all right? If we were in lab every week this semester, there may be times where, depending on what type of instrument you use, you can only report a certain number of decimals, and it does matter in lab, but no, as long as I can follow your work on a problem and you're not, you know, clipping numbers by huge amounts, you know, give me 1 or 2 decimals. But as long as I can follow it and it's clear, I don't care if there's 2 or 3 decimals. But give me a couple. But we're not going over rules of sig figs in this class. Chances are you've seen those in a different class. So, all right, let's look at these. So we've got 7.41 times 10 to the power of 8. So I'm going to move the decimal 8 places, okay? And I'm going to, since I'm multiplying by a very large number, I'm going to move it 8 places to the right. So when you're undoing these, the rules are actually kind of reversed. So it's going to be 7, 4, 1. So I moved it 2 places. I'm going to move it 6 more places, and I'm going to represent that with zeros. 1, 2, 3, 4, 5, 6. Okay, now let's double check ourselves. If the decimal's here and we're converting this to scientific notation, we would move it 1, 2, 3, 4, 5, 6, 7, 8 places and be between the 7 and the 4, and that would be correct, okay? So when you're undoing these, you're just multiplying by a large number here, 10 to the power of 8, and this is the standard number you should get. Any questions there? Okay, here we're multiplying by 10 to the negative 5, all right? So we're gonna move the decimal to the left. Here we move the decimal to the right when we're kind of converting from scientific back to standard. You move it the opposite way. So it's going to be 0.12343021. And let's double check ourselves. Okay, if we move it back 5 places, would we get 10 to the negative 5? 1, 2, 3, 4, 5, and we moved it right? Yes, we would. So that's the standard numbers you should get when you're converting them back from scientific to standard. Questions there? Okay, we're going to move on. So we're going to also look at how to add and subtract, how to multiply, and how to divide numbers in scientific notation. And then we're going to move on to prefixes. And that's the last topic we're going to talk about for today. So addition and subtraction. The rule here, simply put, your exponents have to be the same for you to add and subtract numbers in scientific notation. So I have an example typed out for you, and then we're going to work one ourselves. So let's look at this first example right here. 7.41 times 10 to the power of 8 plus 4.32 times 10 to the power of 10. So you can see my exponents at first, they don't match. I have an exponent of 8 and an exponent of 10. So you just pick one of the numbers. It does not matter which one. In this example, we pick the first number, and we're going to adjust it so that the exponent does match the other number. So we're going to take an exponent of 8, convert it to exponent of 10. Okay, so the way they did that, remember, if you move your decimal to the right, or sorry, if you move it to the left, your exponent increases, right? Let's go back and check our rules. You move the decimal, here it is right here. If you move the decimal left, the exponent increases. So we're trying to increase our exponent 2 places, from 8 to 10. Okay, so we're going to move the decimal 2 places to the left, and that's what they did. The decimal initially was between the 7 and the 4, and they moved it 2 places to the left, so the exponent goes up 2 places. So now we have exponents that match. Now all you do is you can pull out your calculator. You would do 0.0741 plus 4.32, and you should get 4.39. Notice they rounded here. I wouldn't care if you put all the decimals that you could, okay? And then we have times 10 to the positive 10. All right. The reason they only gave you 2 decimals here is because you're limited, okay, by that first number. That's the actual answer for those of you who really want to know. But let's look at this example down below. So we have an exponent of negative 5 on our first number and an exponent of negative 8 on our second number. So I'm going to pick this exponent of negative 5, and I'm going to convert it to negative 8. Now, when you're in the negatives, you have to remember something's different. A negative 8 is smaller than a negative 5. Okay, so that seems confusing. But in world of negatives, -8 is smaller than -5. So -5 here is larger. So we're trying to decrease our exponent. Let's go look at our rules. When the exponent, for the exponent to decrease, the decimal has to move right. Okay, so we're gonna move, we need it to decrease 3 places, so we're gonna move the decimal 3 places to the right. So what you end up with is 3021. There's your new decimal. You can put a 0 after it, that helps. And then that will now be times 10. Now our exponent has changed. It's decreased 3 places, so it's times 10 to the -8. And then our other number stayed the same. We did not have to manipulate it because we are taking the exponent from the first number to match the second. Now to match. Yes, question.
At the beginning of class, you said the base number of this has to be between 1 and 10.
Okay. Yes. Well, we're in the middle of a mathematical process right now. So once we get our answer, then we could convert it back to the general format.
Okay.
Yes. So we're not totally done yet, but hang with me. This is just for the purpose of adding or subtracting them. And then someone said, can you scroll back up just a little one more time? What do you need me to scroll to? Was it the rules?
Yeah, it was just the examples and the rules. Mm-hmm.
Okay, there's the rules.
Thank you.
Okay, so let's go back to this. So now we are going to add, I'm just going to grab my calculator. So I'm going to do 3021 minus 2.86. And I get 3018.14. And my exponent as it stands now is 10 to the -8. Now, again, we do want this to be a number that is between 1 and 10. So I'm going to move the decimal 1, 2, 3 places back to the left. And what happens when you move it to the left? Let's go check our rules. The exponent increases. So we'll actually, this will increase. It'll go back to negative. So it would be 3.01814 times 10 to the -5. So probably a shorter way around now that we finished the problem. The shortcut to this would have been to take the second number and modify the exponent to match the initial, okay, the -5. We didn't do that. We picked it random. We picked the first number. So that's why at the end we had to go back and change it back into a number between 1 and 10. Does that make sense? Any other questions? All great questions. Okay. So multiplication. This is a little more simple. You just multiply the digits and you add the exponents. You don't have to mess with moving decimals, okay? It's a little easier. So you just throw in your calculator. In fact, I'm going to let y'all type it into the chat. Let's do 7.41 times 4.32. What do we get? What's our new base number? And don't convert it or anything yet if it's not a number between, looks like it's not going to be a number between 1 and 10. But just what is it? Should be close to 30. $7.41 times 4.32. Anybody get it? 32.01. Okay. I'm gonna roll with that unless somebody wants to argue. Okay. Good. All right. And then we're gonna add the exponents. 8 plus 10. So it should be exponents 8 plus 10. And you're going to get times 10 to the 18. All right, now this is not a number between 1 and 10. So we're going to convert it to a number between 1 and 10. We're moving the decimal 1 place to the left. Remember, when it moves to the left, the exponent goes up. So it's actually 3.201 times 10 to the 19th. Questions there? Okay. And then I'm going to give you a second. Start working on the last one. Same thing here. You're just going to multiply your base digits and then you'll add your exponents. Just remember your exponents are both negative here. Okay, what's our new base number? Anybody get it? 3.021 times 8.64. I'm going to go with that. Thank you, Abby. And then it should be times 10 to the negative 13. Okay. Now I know those exponents are pretty large, right? But don't let that freak you out. That's when you multiply numbers with exponents, you get numbers with even bigger exponents, okay? All right. Last thing with scientific notation, then we're moving on. How to divide them. So the rule here is you divide the digits, you subtract the exponents, okay? I would make sure you have these rules down. One, for the quiz Thursday, you might see a problem like this, one of these kinds of problems on the quiz. Also for the exam, okay? I want to make sure you can manipulate these numbers before we move on into next chapters, all right? Divide the digits, subtract exponents. So here, 7.41 divided by 4.32. So you would just put that in your calculator. Are we allowed to use our notes on the quiz? If you watched my short little video about updates on the syllabus, thank you, Brennan, I'll write that down. The quizzes and the exams, I mean, if I'm not using Respondus browser and everything, then yes, it's open note, open book. But here's what I'll tell you. That doesn't mean that you don't need to know the material, because you will be timed, okay? And I'm not going to give you crazy amounts of extra time because I want to make sure that you know the material, and how can I help ensure that? So if I give you all day to take a quiz and you have all day to use your notebook, I don't know that you know this stuff. So please still know it. If you need to refer to your notes, yep, you'll be able to, because I'm not using like the browser lockdown and Respondus stuff. So, okay, the answer here is, whoops. Okay, hold on, equals 1.7. Well, look at all those decimals, 5, 2. We'll just use them all. And then we subtract the exponents. So we have 8. Exponent-wise, we have 8 minus 10. So you should get times 10 to the negative 2. And our number is already a number between 1 and 10, so we don't have to do any further manipulation. That's the things that people miss. They'll do the problem right, but then they'll forget to change it to the correct format, which is a number between, or your base number should double check that your kind of your base number here, what I've underlined, is between 1 and 10. All right, last one, last practice, we have 3.021 divided by 2.86. So you're going to write that base number down. Anybody get it? $1.06, and then you're going to subtract the exponent. So here we have negative 5 minus a, don't forget the negative on the 8. And remember, a double negative makes this a positive. So this is negative 5 plus 8. And you should get positive 3 for your exponent. So times 10 to the third. Okay, questions there? Brennan, even, okay, that's too many decimals at that point, Brennan. All right, we're done with scientific notation. Take a breather, grab a sip of coffee. We're gonna move on to the next topic. Prefixes. This is where this class gets hard for some people. Some of you have seen this before. I will tell you before we get into this, if you've seen this in a chemistry class before, you may have learned it differently, and that's okay. People teach this stuff many different ways. I'm going to teach it here's the way I teach it, but if you're watching YouTube videos and you see it taught a different way, there's so many ways to use prefixes and later on use them in conversion factors. So it's okay if you're like, well, I understand what you're saying, but I like to write it this way. As long as it means the same thing and the relationships are the same, that's okay with me. Okay, but if you ever have a question, shoot me an email. But let me introduce prefixes. First off, just in the English language, what is a prefix? I'm going to zoom in up here to write my example. It's a word that comes before another word, and it adds meaning, okay? So if I say Jordan, you don't know who I'm talking about. If I'm in a room with Michael Jordan and Jordan Sparks, that would be a fun day, right? You don't know who I'm talking to. If I say Mr. Jordan at that point, you understand I'm talking to the Michael Jordan. If I say Mrs. Jordan, is she married? Is Jordan Sparks married? I don't know. Not, she should be. Then, you know, I'm trying to sing Noette, No Air Duo with her, all right? Speaking of, Michael Jordan. Anybody? We don't really watch a lot of sports. My husband doesn't. We actually don't even have a TV. I know. But anybody who's big on their sports and their Michael Jordan, there was a documentary. I don't know if it's a Netflix documentary, The Last Dance. Anybody watch that? Anybody big into sports? So it was so good. He thought it was too. So that, I don't know when it came out, but I know like my husband got real interested in watching it right around the time we had our son this summer. We had him back in June, June 7th. And y'all know that newborns don't sleep super great. So I was like, praise the Lord. Because every single night when I was like crashing, my husband would be like, I got him. We're gonna go watch The Last Dance together. And so that he would just take him at like 10 p.m. and let me go sleep until he was ready to eat again. So I'm very thankful for that documentary is all I'm trying to say. But my point here is that prefixes are words that come before another word and they add meaning. And it's the same idea in chemistry. All right. The reason we use prefixes is right here. Scientists often deal with very small or large measurements, right? And they can make our head spin. I mean, look at this first one, a virus particle. This is the one this is the most applicable thing I'm going to say today. Look how small it is, okay? This is what is destroying our universe and our culture and our lives right now. Something that is this small, guys, this small. Okay, I'm going to erase that, sorry. But it is 0.000000120 meters in diameter, all right? If we're talking about the distance to the sun, we could say it is that many meters, a lot of meters from the earth to the sun, all right? But it's hard to look at numbers like that with that many zeros and comprehend it, okay? So we use prefixes to help make numbers manageable. And also you'll realize I have a very hard time speaking and spelling. So if I ever misspell something, just laugh at me and move on. And it gives reference, all right? So now we have actually inserted a prefix here. You may not know what this prefix is yet, and that's okay. But if we communicate with the prefix of NM, all right, a virus particle is now 120 NMs. Does anybody know what NM is? What prefix we've applied here? You don't have to. Nano, okay, nanometers. All right, so nano is the prefix that we put in front of the word meters, and it changed the size of the quantity, all right, because of the prefix. So if it's 120 nanometers, but it's 0.000000120 meters, a nanometer is way smaller than a meter, okay? But we can talk about it in a manageable number as long as we talk about it in nanometers. Same thing, if we talk about that second statement, we could say it's 150,000 capital M, lowercase m. Anybody know what the capital M stands for? Any guesses?
Millimeter.
Wrong, but good guess. Mega. Okay, it's 150,000 megameters. So a megameter is a lot bigger than a meter. So it takes fewer megameters to get to the sun than it does meters, okay? A nanometer on the opposite scale is a lot smaller than a meter. So a very, very, very small amount of meters is actually a decent size of nanometers, okay? Also, we could talk about it with km. Anybody recognize km? That one's a little more familiar.
Kilometer.
Yes. Kilo or kilometer, however you say it. All right. It threw me off the first time I was driving around. You know how people put like anybody a marathon runner or a runner in this class? You know, people put the 26.2 stickers on their car. Well, the first time I saw like a 45.4 or whatever, I was like, what in the world is that? Somebody's running 45 miles, which people do, and it's crazy. But over in like Europe and stuff, they communicate in kilometers. And so that's just the distance from marathon in kilometers. All right, let's move on. So continuing with our talk about prefixes. Prefixes, like I said, they're words that you put in front of other words. And for this class, you're putting them in front of base unit words. So what in the world is a base unit? Well, there's actually three that we're going to use mostly in this class. Okay, the first one would be a gram, a unit of mass. Second would be a liter, unit of volume, or a meter, unit of distance. So these are the 3 base units that we are going to work with in this class. You need to get real. When I say base unit, you should think gram, liter, or meter. Now, listed below is all your prefixes. Now, you're not going to have to memorize all these, but there are like 4 that I'm going to ask you to know because they're pretty common. So let's just go through this at first. So I wanted to divide this figure. You see, I've put a red line here. That's because these 3 words, these 3 prefixes above the red line, these prefixes make the quantity larger. Okay, so these right here make the base unit larger. Okay, in other words, they're larger than the base unit. And we're going to fill in the blanks here to see how much larger. So 1 kilo, if I said a kilogram or a kiloliter, is 1,000 of your base units. So a kilogram is 1,000 grams. And you guys are actually more familiar with this than you think. If I told you I went out and bought a car for 5K, all right, people communicate money like this all the time. How much money did I spend on the car? What would you tell me? You'd probably tell me, well, you ain't going very far because that's a cheap car. But I spent $5,000, right? So you understand what K stands for. And it's the same here. It makes it bigger by 1,000. 1 kilo of anything is 1,000 of that base unit. Okay, hecto, we abbreviate it with an H. It is 100 base units, so it's only 100 times bigger. So 1 hectometer is 100 meters. 1 hectogram is 100 grams. Okay, deca. You guys are familiar with this. How many years is a decade? 10. So 1 decagram is 10 grams. 1 decaliter is 10 liters, okay? All right, those are the 3 that are bigger than the base unit. The ones below the line, these are smaller than base unit. And I actually don't like the way I wrote this up here. I'm going to rewrite this. I don't like the way I said make up the base unit larger. I'm just going to say they're larger than the base unit. I don't want that to be confusing. Okay, these are larger, down below they're smaller. So now because these prefixes below the line are smaller, we're going to see how many of them are needed to equal 1 base unit. Okay, so deci, well, there's 10 decigrams or decimeters in a gram or meter. There's 100 centimeters in a meter. Okay, milli, it's smaller by 1,000, so there's 1,000 millis in 1 base unit. We abbreviate this with an M, lowercase m. Now we also abbreviate meter up here. We abbreviate meter with an M, okay? So don't get those confused. If you see M, when we use abbreviations, we're talking about a millimeter. They're both abbreviated with an M. But if you just see 1 M, then we're just talking about meter, okay? Micro, there's 1,000,000 micros in a base unit. And let me point out this abbreviation because it's definitely the different one, okay? It is a U, but do not forget this front little tail, okay? So it looks like this. So that's the abbreviation for micro. If you just write U, that's incorrect. And then nano, I think it's 1 billion. That's 9 zeros, right? Yeah. Okay. So nano is really, really, really small. 1 billion nanograms is 1 gram. 1 billion nanoliters is 1 liter. All right. And notice these base units up here, any of those words could be substituted in this side over here. All right. Questions on prefixes so far? That's one way to write them with all these zeros. This next slide is just to show you can write them in scientific notation and it's a lot less zeros. Okay, so all this information on this slide right here is the exact same information. Now notice there's a few we're missing, like deci and deca and hecto, but these are the common ones that we're going to use in the course. Kilo, centi, milli, micro, nano. Okay, so instead of just writing this is 1,000 base units, we just wrote 10 to the power of 3, so on and so forth. Okay, questions so far? All right, we're going to continue to talk about base units for a second because I want you to have a feel of how big, if I say liter or if I say gram, I'm sure none of us, even me, have to think for a second, well, how much is a gram? I don't know. So I'm going to give you some very tangible examples so that if I say the word gram, you know a gram doesn't weigh very much, okay? Or if I say the word kilogram, you know I'm talking about some more mass. So let's look at some practical examples. First, we're going to start with the base unit of length. Length is a measure of distance. We know that. And the base unit is the meter. Now, we may not, since we don't use meter a ton, common in our English language, we use yard more, all right? Well, I want you to know that 1 meter is approximately 1 yard. If you watch football, you know about the distance of a yard. If you have a yardstick at your house, okay? 1 meter and 1 yard are just about the same. All right, so that's how big a meter is. Let's keep going. What about a centimeter? Okay, a centimeter is approximately, so here's a ruler and we've zoomed in on centimeters. You can see a centimeter is about the width of your pinky. Now, I know everyone's pinky is a different size and that varies. I'm not even kidding. My husband's grandfather wears a size 15 ring. He has dealt with like windows and glass stuff his whole life, so his fingers are like super big. So not his pinky, but about the size of your pinky. That's the width of a centimeter. Okay, what about a millimeter? That, if you look one from here to here, that is a millimeter. Okay, that distance is, I'll zoom in, it's very, very small. That's a millimeter. It's about the width of your pencil lead, okay? So it's very, very small distance. Again, I'm just trying to give you tangible so you understand how big these units and prefixes are. This next slide is just a table that is also in your textbook. So as you work problems, now you can Google stuff, you have access to that. I'm asking you guys not to use the internet on exams and on assignments. You can use your textbook, you can use notes, but I'm gonna have you sign academic integrity forms that you will not use the internet, okay? That is to your disadvantage. You are cheating yourself if you're just Googling things and writing down what Google says, okay? So these tables are important because they're in their textbook and they give you the equivalents and conversions for lots of different stuff. So refer to this as you need to in chapter 1. And that's all for length, okay? All right, so we're done with length for a second. Let's move on to the base unit mass. So that was our second base unit. First off, mass and weight are different. And then secondly, mass is the amount of matter. Remember we started off last week talking about matter? The amount of matter in an object, all right? Weight is different. How is it different? Weight is a measure of gravitational pull. Your weight is different if you're on the moon versus if you're on planet Earth, but your mass is the same. You have the same amount of matter in you if you're on the moon versus if you're on the Earth, okay? Base unit of mass is the gram. Now, how much is a gram? Okay, well, if you see in this picture, we have put a dollar bill on a balance, and you can see it weighs a little over, but about 1 gram. And think, a dollar bill doesn't weigh very much. So you can understand a gram doesn't weigh very much. How much is a kilogram? A kilogram is 1,000 times, and it's roughly the weight of a loaf of bread, okay? Now, y'all know I love to talk about food. I always do at any point I can. If you have not had Dave's Killer Bread, okay, y'all are all health professionals. Buy the stuff that do good for your body. This is the best bread. I'm not even kidding. I would eat a slice of this bread by itself as a snack. It is that good. Look at that, 21 whole grains, okay? Now let me tell you, you will pay for it. It's not cheap, but you go to Sam's, you get a good deal on it, all right? Find somebody who has a Sam's account. If you're like, I don't have a Sam's account, loaf of bread. All right, so again, I'm just trying to give you tangible so you know about how much a kilogram is, loaf of bread. So if I ask you, you know, what's the most appropriate, we're talking about a watermelon, you know, what would be the most appropriate unit to talk about the mass of a watermelon? Grams or kilograms? Probably kilograms, okay? A watermelon would be a ton of grams, but it would be fewer kilograms because kilograms are bigger. All right, move on. Here's the same table, but for units of mass in your textbook. Shows you all the equivalents for and relationships between grams, kilograms, pounds is on here. Ounces is on here as well. And what else? I think that's mostly it. Milligrams, micrograms. All right, so that's it for mass. Last thing, we're gonna talk in depth for a second about volume, and then we're actually gonna work some simple conversion problems using prefixes. All right, and then we'll be done. Volume, measurement of the space occupied by an object, okay? Base unit is the liter. Now, we measure volume with pieces or instrumentation that look like this. This is a graduated cylinder. If you've taken a science class in high school or so, you probably recognize this. And I just want to take a minute to remind you, even though we may not be in the lab very much this semester, it's still important for you to know how to read these things. If you'll notice, any liquid you put in these instruments is going to be curved at the top. And how do you read this? Do I read it over here? Do I read it right here or over here? You read it what we call the meniscus, the bottom of that curve. All right, that is the meniscus. That's how you read volumes in volumetric instruments. Okay, but going back to, well, how big is a liter? This is actually one we're pretty familiar with. We can buy sodas and Cokes in a 1 liter bottle or a 2 liter bottle. So you're probably familiar with about how big a liter is. But the English comparison is it's about a quart. Okay, you can go buy a quart of oil. Now, I did not put a picture of a quart of oil because y'all know I love ice cream. A quart is 2 pints. Okay, so here's a pint of ice cream, and a quart is 2 pints put together. And I just wanted to introduce my favorite ice cream to you. And so here it is, Jenny's ice cream, everyone. We don't even have a Jenny's storefront in Arkansas. It's very sad, I know. Now there are some like bougie grocery stores that sell this stuff for like $8, $10 a pint. But you can go buy a pint of Halo Top or cheaper ice cream at Walmart. You understand how big a pint is. 2 pints is a quart, and that's about 1 liter, okay? Trust me, though, it's worth it. Go try some Jenny. It's like the best ice cream in the world, I promise. All right. Volume, how big is a milliliter? Well, if a liter is about the size of corn, a milli is 1,000 times smaller than that. It's about the size of your pencil eraser. Again, you can say the width or about the volume of the tip of your pinky, but everyone's pinky is a different size. So if we're all going to be on the same page here, just say pencil, volume of your pencil eraser. And I'm talking about a regular standard ACT pencil here. By the way, I heard that colleges are like looking at ACT scores less and less as a measure, as a metric for like, I don't know, your IQ to come into college. I heard they're looking at your GPA more. Praise the Lord. Everybody hates the ACT. Last one. No, here. So we've got, it wrote tip of pinky here. We could write pencil eraser. Okay, on this slide, nothing is really different except for the fact that I want you to know this relationship. I mentioned that we can measure volume in liters, milliliters, that system. We can also measure volume. If you remember the international system, SI units, they measure volume as cubic distances. And that's what you see here. When you have shapes that are easy to measure with a ruler, like a cube, it's easier to just whip out a ruler and measure the cubic distance and get the volume that way. So if I have a cube that measures 1 centimeter on each side, I have a cube that is 1 cubic centimeter. Now, the fact that we put this 3 right here as the exponent indicates to us that it is a cubic distance. Okay, I'm going to erase because it's kind of getting crowded to see. A cubic distance. So this is a cubic distance. Milliliter, ml, is the metric unit for volume right here. I want you to know this relationship. 1 milliliter and 1 cubic centimeter, those are about the same. So a cubic centimeter, again, it's about the size of your pencil eraser or the volume of your pencil eraser. 1 milliliter is 1 cubic centimeter. This is especially going to be important when we talk about density. And Thursday, we're talking a whole lot about density. So know this relationship, 1 milliliter, 1 cubic centimeter. Know it, memorize it, say it in your sleep. Know it. This is just this next slide. I'm really not going to talk a lot about it, but for those of you who just want a better visual about how cubic distances relate to liters and milliliters, this slide does that for you. If you had a cubic meter, okay, and then you broke it down into smaller cubes, and then you took one of those cubes and had a cubic decimeter, and then broke that down into 10 equal pieces on each side, took one of those cubes, here's your cubic centimeter. Well, it's not letting me write. There it is. And again, 1 milliliter, 1 cubic centimeter. This gives you other relationships, but you don't need to memorize those. You don't need to know those. The only one I want you to know is 1 cubic centimeter is 1 milliliter, okay? And then here's that same table for volume in your textbook, okay? Lots of different equivalents for you to use as you work problems. It's got quarts on there. It's got fluid ounces on there, gallons. If you need an equivalent for gallons, it's got gallons, so on and so forth. Okay, here's where you really need to pay attention. Which of these are so common they will not be given to you? Now, obviously, I recognize you can flip to your textbook. You can flip to your notes. But I'm asking you to take the time to memorize these as you move forward in your education as a health professional. It's going to service you, especially you nursing people and dietetics people, sports medicine people, exercise science. It's going to benefit you to know these terms, okay? So kilo, know kilo and how it relates to the base unit. Need to memorize that. And then centi, milli, and micro. So these three down here. I'm not asking you to memorize the relationship from nano. If I want you to perform something on an exam with nano, I'll give you the relationship. I'll say a nano is 10 to the power of 9 grams or whatever. So those four, kilo, centi, milli, micro. Familiarize yourself with those relationships or those prefixes and their relationship to the base unit. Questions so far? Okay. We have roughly 10 minutes left, and we are going to try to start doing some conversions. And then whatever we don't finish on the conversions, we'll just pick up there on this lecture Thursday, okay? But I promise you on exam 1, you will have some complex conversions, okay? These are simple conversions that we're starting out with. 1-step conversions, 2-step conversions. We are going to work our way by the end of Thursday to handle complex conversions, which are word problems, and they have 5 or 6 steps. So really zone in for the last 10 minutes, give me everything you got, and we are going to start working some problems. But before we do a conversion problem, what is it saying? We've been talking about prefixes. Now we're going to learn how to use prefixes as conversion factors. So using conversion factors to obtain an equivalent quantity in a different unit. Now, what in the world does that mean? You're actually way more familiar with doing simple conversions in your head than you even think. If I told you, hey, I need you to go to the store and buy 144 eggs. If I told you that. Well, they don't sell eggs individually, right? They sell them in dozens. So you actually already do this conversion in your head. You would need to know, if you know the conversion, the relationship that 1 dozen is 12 eggs, you've already done a simple conversion, okay? So if I say I need 144 eggs, you're going to, they sell them in dozens, so you need to know how many dozens is 144 eggs. So you would do that conversion. Okay, that's 12 dozens. I'm going to go buy 12 cartons of eggs, all right? That is a simple conversion that we didn't even have to put pen to paper for, all right? It's just that in chemistry, these prefixes, nano and centi and milli, they're less familiar to you, so that's why sometimes it seems like a foreign language, but you just got to practice it, okay? So a lot of this will be on your chapter 1 homework. There's many ways you can write conversions factors. Now, what is a conversion factor? Well, where was my? It is the relationship between, I'm going to abbreviate, 2 units. And we just talked about that with the units of eggs and a dozen, okay? It's the relationship between 2 units. So there's multiple styles and ways for writing out conversion factors, and that's what you see here. I can write it this way: 1,000 grams equals 1 kilogram. That's a conversion factor. Or you can write them actually as factors. In the world of math, a factor is a numerator and a denominator, okay? I encourage you to write them out like this. And you can write it 2 ways here. We have 2 numbers. You could put grams on top, or you could put grams on bottom. Either way, this is the same relationship. They both mean this thing over here on the left, that 1,000 grams is 1 kilogram. All right. Now, if I ask you the question, 1.36 kilograms is how many grams. Now we have to use one of those conversion factors to get our answer. Always start with the number that's given. Here we're given 1.36 kilograms. So I'm going to write that out, 1.36 kilograms. To get it in grams, I have to, what they call, cancel out kilograms. And this goes right along with the word of the day. This is cancel culture, everybody. Okay? We're going to cancel out, we're going to cancel kilograms. So if I'm looking at these factors over here, I'm going to write it as a factor. And I want to cancel kilograms. Right now, if I were to draw a line, I have kilograms on top. I want to pick the conversion factor. I'm converting to grams. That is going to let me cancel kilograms. I want kilograms on bottom. So I want this conversion factor right here. I'm going to write it just as is, 1,000 grams over 1 kg. Now, in the world of math, you have a unit on top and you have a unit on bottom. You can cancel. You can cancel kilograms. Okay? When kilograms cancel, what unit do I have left? And more importantly, I want that unit on top in the numerator. That's important. I have grams in the numerator. So now I do math. 1.36 times 1,000, and my unit here is grams. I have converted successfully to grams. So that's 1,360 grams. Questions on that simple conversion? Okay. Let's see. We really don't have as much time as I was hoping. You can notice that I have put several simple conversions on here. Let's do one more in centimeters, and then I'm going to actually pick a conversion from one of these slides down here, and then we're going to be done. I think we have time for 2 more in the amount of time we have left. And I'll take questions as well. Go back to pink. Okay, let's look at this bottom. I'm going to skip meters. We're going to come down here to liters and milliliters. So I have the relationship. The question is 1.23 liters. How many milliliters is that? Okay, so I'm trying to convert from liters to milliliters. So I need a relationship between liters and milliliters. And that relationship is written right over here for you. 1 liter is 1,000 milliliters. Okay, and if you're like, how did you get that information? That was on one of those slides earlier in the lecture where we introduced prefixes. Now, I want you to write it as a factor. Well, there's 2 ways you could do that. You could put liters on top, or you could put liters on bottom. And we'll pick one of these 2 in just a second. So I'm going to start with my number given. I'm going to do the conversion problem now. I'm going to convert from liters to milliliters. So if I have 1.23 liters, I have a little bit over a liter. How many milliliters is that? Right now I have liters on top. I'm going to multiply. I'm going to pick one of these conversion factors. Which one is going to let me cancel liters, and it's going to leave me with milliliters on top in the numerator? The answer is this one right here. So we're going to multiply. We're going to write the conversion factor just as is, 1 liter on bottom, 1,000 milliliters on top. And you see we have liters on top right here and on bottom, so those cancel. Now we just have a math problem. 1.23 times 1,000 is 1,230 milliliters. Okay. Questions? I'm looking at the chat. I don't see anything on the chat. Any questions from anybody on how we started to do these simple conversions? Okay, if this is challenging for you, please reach out to me and let's chat. Don't wait till next week. If this is like, oh, easy peasy for you, why don't you go ahead and try some other ones in your spare time? I'm going to pick one more problem. Let's see. You know what? We're going to do one that looks kind of hard. This is the last problem we're going to do for the day, and then we'll do more Thursday. I want to do this one right here. We have, how many of this? 578,965 ng. What is an ng?
A nanogram.
Mouthing it, yes, a nanogram. Thank you. Okay, nanogram. Now, if you remember, a nano is really small. When we converted that virus particle to nanometers, we realized nano is a prefix that's way, way, way smaller than the base unit. So we need a relationship between nano and micro. Well, if I go, I don't want to make you all dizzy, but if I go way up to that slide that shows all those relationships, what I see is 10 to the 9 nano. Here, I'm going to write grams equals 1 gram. That's my relationship, 10 to the power 9, a billion. Well, I don't have a relationship that lets me link directly to micro just yet, but I do know how many micrograms is in a gram. I know there's 10 to the 6th. Micro, remember micro is that funny looking U. Microgram is 1 gram. And I'm just pulling this information from one of those previous slides that had them listed out that we talked about earlier when we just first introduced prefixes. Now, you can do this problem one of two ways. You can use both of these steps. You can use step 1, convert to grams. Then you can use step 2, convert from grams to micrograms. Or you can do it in one step. We just need to write one more relationship. How many micrograms is in a nanogram? Well, to find that out, you're going to look at the difference between these two numbers. I have 10 to the 9 and 10 to the 6. What's the difference here? 10 to the power of 3. And you got to know which unit is smaller. Here, nanogram, nano is the smallest, okay? So that means there's more nanograms in a microgram. So that means there's 10 to the 3 nanograms in 1 microgram. Now, if what I just did lost you completely, you don't have to use this relationship. You can use the 2 we wrote out earlier. Or you can do it in one step using what we just wrote, okay? So I'm gonna erase this box because it's kind of getting in my way. So now let's solve the problem. I'm gonna show you both ways. We'll do the 2-step problem first. I'm gonna write my number given right here, start with that, 5. I'm gonna zoom in. What was it, 578, 965, 578, 965, and that is nanograms, and I'm trying to get to micrograms. So I'm gonna use this relationship first. I'm working it as a 2-step problem first, and then you'll see how it's simpler if you do it as a 1-step. So we know I'm going to write this as a fraction, and I want to cancel nanograms. So I'm going to write 10 to the 9 nanograms on bottom, 1 gram on top, and then nanograms cancel. See how they cancel, top and bottom. Now let's keep going. I'm just going to keep going because I'm not at micrograms yet. It wants the answer in micrograms. So I got to come use relationship number 2. And I want to cancel grams this time. I don't want grams in my answer, so I'm going to cancel grams now. So there's 10 to the power of 6. 1 gram was 10 to the power of 6 micrograms. And now you see grams cancel as well. Okay? And then you have your answer. You just do the math now. You do 578,965 divided by 10 to the power of 9, multiplied by 10 to the power of 6. So what you should get, I think your answer, correct me, put this in your calculator, but I got 578.965 micrograms. Is that what y'all got? Nobody is disagreeing with me. We're almost done. I know we got 1 minute left. I'm watching the clock. All right, now let's do it with this third relationship. This is going to be a 1-step problem this time because we have a relationship that lets us go directly from nanograms to micrograms. So I'm going to start with the same number. Now I'm going to use this relationship over here. I'm going to cancel nanograms, so I'm going to write it on the bottom. There's 10 to the power of 3. That's 1,000 nanograms in a microgram. You can write 1,000 or you can write 10 to the power of 3. Same thing. Nanograms in 1. Remember, micro is the U with the fun tail on the front. And you see, when we write it like this, nanograms cancel. So I'm dividing this number by 1,000, and you should get the same answer. 578.965 micrograms. And these answers right here are the same. And notice we got to write our units every single time. Any questions? Okay, well, that's it for lecture today. I challenge you, there's a table right here. We almost got to it. Try to fill this in for me, just to summarize what you learned. If you'll do that as soon as you hop off the Zoom, it'll help you just recap and digest the overall big picture things we learned today. Yes, I will check my email when I get time. If you sent me an email yesterday, I have not responded. I have likely read it, and I will respond today for sure. I will get to you. And any other questions? If you have questions, hang on for just a minute, and I'll stick around and answer those. If not, lecture's over. Thanks for joining today. I will post the lecture hopefully by this evening or tomorrow on Blackboard. Y'all have a good one.
I have a question
Oh,
about the quiz. Sorry.
Yes.
So you said the quiz is on Thursday. So can we wait to take the quiz after lecture on Thursday?
Yes, you can. It'll
Okay.
be open till 5 p.m.
Okay.
You can get on and take it. You've got other classes and other things, so that's why I'm opening it up at 8 a.m. if people need to get it done early. But it will be open till 5 p.m. And so you'll need to, at the latest, I don't know how much time I'm going to give you just yet. I'll let you know in an email. But you'll need to start it by probably plan to start it by 4 p.m. so that you get it done for sure by 5.
Will it have information from Thursday's lecture or no?
No. If you want to take it early, all the information we've covered between our first 2 lectures, I'm not going to put any information or material from Thursday's lecture on the quiz. It'll just be material from our first 2 lectures. Good question. Any other questions? What will the format be? 5 multiple choice. 5 multiple choice questions. Now, I would have a calculator ready to go, but 5 multiple choice. All of our quizzes, all semester long, will always be 5 multiple choice. Any other questions? All good questions. Well, I'll stick around if there are. Not, thank y'all for joining. Y'all have a good one.
I have a quick question.
Yes.
So unless I've missed something, I noticed, I was able to get into the Pearson Mastering course and all that.
Yes.
And so one of our assignments is like Chem Primer or something like that.
Yes.
What exactly is that? I think I just missed something because I don't.
It's just to kind of familiarize for some people. It's been a while since they've had chemistry, and it is just to familiarize you with the language of chemistry. And in fact, you're not penalized for any of your responses on the primer. It's pretty much if you complete it, you get the points type of thing. You get multiple attempts to do it. There's kind of like a little mini lesson for each thing. It walks you through some material and then it poses a question on that material. So it will have you do conversion style stuff. It might introduce density. It might introduce concepts that you're like, I don't know what this is, but just attempt it. That is actually going to be beneficial for you. It might seem challenging to some people that are brand new or haven't had chemistry a long time ago. But it's just to get you kind of, maybe you've heard some of these words before. And you're like, oh yeah, I remember what density is. Or, oh yeah, that's the purpose of the primer. Okay. Kind of just to prime the pumps, as they might say, if you're a mechanic, on some chemistry terms.
All right, thank you.
You're very welcome.
The homework on mastering, can we, do we have to do it in one sitting, or can we go and do some and then
No,
go?
Yes, you can come and go as you need. It is not timed. Our Blackboard assignments, like our exams and our quizzes, will be timed. You need to sit down and get it done, and that's on purpose. But homework, you could attempt some. You could reach out to a friend, say, hey, I'm trying this problem. What did you get? Or you can email me, hey, I got stuck on this. I just wanted to talk about it. You can go eat dinner. You can come back. You can do it over multiple days, okay? So you don't have to sit down and get it done all at one time.
Okay. And then will there be a quiz for each chapter or multiple quizzes per chapter?
Usually, Kate, it's 1 per chapter. So I have scheduled point-wise for us 10 quizzes. So 50 points from the course is quiz points. So that's, when you realize that's half an exam. All of my exams are 100 points. So I would definitely take the quizzes serious. There's usually 1 per chapter, though. So this will be our chapter 1 quiz, and then next week we'll have our chapter 2 quiz.
Okay.
Yep. All right, Kate. Do you go by Kate or you go by Caitlin?
Kate.
Okay. All right. Okay, well, it looks like it's just you and me, so I'm going to hop off, and you have a good one.
You too.
All right.